Hello and welcome to Lecture 5 of CS 301 Systems 4 course. Today we shall be talking about properties of concurrent programs. The requirements for a concurrent program can be defined in terms of properties that it must possess. If the properties are expressed formally, that is mathematically, then it may be possible to verify formally that an implementation has these properties. Many properties can be classified as either a safety or a liveness property. Safety property. Safety properties assert what a program is allowed to do or equivalently what it may not do. For example, mutual exclusion. No more than one process is ever present in a critical region. No deadlock. No process is ever delayed awaiting an event that cannot occur. Partial correctness. If a program terminates, the output is what is required. A safety property is expressed as an invariant of a computation. This is a condition that is true at all points in the execution of a program. Safety properties are proved by induction. That is, the invariant is shown to hold true for the initial state of the computation and for every transition between states of computation. The second property is liveness property. Liveness, or it is also called as progress, assert what a program must do. They state what will happen eventually in a computation. For example, fairness. A process that can execute will be executed. Reliable communication. A message sent by one process to another will be received. Total correctness. A program terminates and the output is what is required. Liveness properties are expressed as a set of liveness axioms, and the properties are proved by verifying these axioms. Safety properties can be proved separately from liveness properties, but proofs of liveness generally build on safety proofs. So the next video will be talking about in details about the liveness and the safety property. Measures of concurrency. Concurrent behavior can be measured in several ways. In practice, the measures are merely rough classifications of behavior that help characterize a program. These measures are given names here for convenience, but there is no consensus on naming. In particular, references to the term grain or granularity of concurrency in the literature may mean any of the following measures. The unit of concurrency is the language component on which process behavior is defined. It may be an element in an expression, it may be a program statement, but most commonly it is a program block. The level of concurrency is the mean number of active processes present during the execution of a program. The scale of concurrency is the mean duration or lifetime of processes in the execution of a program. There is an overhead in initiating a concurrent activity, and so ideally its duration should be sufficiently long to make that overhead negligible. And finally, the fourth measure is the grain of concurrency, which is the mean computation time between communications in the execution of a program. This should be relatively large if a physical distribution of processes is required. Most commonly, a concurrent program starts as a single process and subdivides into multiple processes at some point in its execution. The spawned processes may be activated individually or in sets. The processes thus activated may be able to subdivide in the same way. So there are main two models of execution. The spawned processes, when activated, execute independently of the process that triggers their execution. And the second, the triggering process forks into multiple processes which, when complete, join to form a single process again. Most programming languages support the fork and join model. Process states. A process exists in one of the three states. Awake, meaning that the process is able to execute. It is a live process. It is awake, so it is in the process. It is able to execute. Asleep, or it is a blocked process, meaning that the process is suspended, awaiting a particular event. Example: message arrival or resource availability. If no resources are available, the process may go to sleep, or it may wait for some message to arrive, and based on the arrival of that message, the process will again awake and start its execution. Or finally, the process can be terminated. Terminated meaning that the execution of the process has finished. So it could be a successful termination of a process or unsuccessful termination of a process. So the processes that are awake can be further divided into those that are running and those that are ready to run as soon as the processor becomes available. Concurrent behavior may be expressed directly in a programming notation or implemented by system calls. In a programming notation, a process is usually described in a program block and process instances created through declaration or invocation references to that block. Process interaction is via shared variables or by message passing from one process to another. Programming languages tend to support only one of these approaches. Shared variables are manipulated in a critical region, acquire exclusive access to region, and then they release the exclusive access to region. Entry to a critical region can be controlled by a status variable that indicates whether or not the region is currently occupied by a process. The status variable itself requires exclusive access. This can be handled by an atomic operation that both inspects and sets the variable without interruption. Most computers provide such an instruction. The status variable mechanism is simple to understand and implement. However, it is insecure and also potentially wasteful because it encourages busy waiting. So, as a part of interaction via shared variable, status variable forms an important part. Next, we talk about semaphores. A semaphore can be regarded as a high-level abstraction for the status variable mechanism. Entry to and exit from a critical region is controlled by capital P and capital V operations, respectively. The operations can be read as wait if necessary and signal. The letters actually represent Dutch word meaning pass and release. Some semaphores are defined to give access to competing processes in arrival order. Semaphores are the most commonly used mechanism for controlling mutual exclusion. There are, however, insecure and also too restrictive because they cannot be inspected directly. The third method, conditional critical regions, improves on the recognized deficiencies of semaphores. Variables in a critical region are defined as a named resource. Critical regions are then preceded by the appropriate resource identification and a condition to be satisfied before entry can be effected. And last, monitors. A monitor improves on the conditional critical region construct by combining regions that use the same resource in one program block, and the monitor is less convenient for the program developer. However, because the suspension and reactivation of processes awaiting a process event must be performed explicitly. A monitor provides a set of procedures through which operations on shared data are performed. The execution of one procedure by any process causes all other processes attempting entry to the monitor to be delayed until the first process has finished or has been suspended. And finally, interaction by message passing. Communication may be synchronous or asynchronous. Processes can name a shared communication channel, or processes can communicate asymmetrically with only the sending process naming the receiver. The basic communication mechanism allowing exchange of information is called a rendezvous. Concurrency also supports the rendezvous concept, but in addition permits asynchronous communication in which the sending process is able to proceed without waiting for data supplied to be accepted explicitly. Thanks for watching this video.